guess you noticed that I posted the Chapter 14 assignment. I changed the due date, which was today, till tomorrow at midnight for the Chapter 13 assignment. And so a week later, the Chapter 14 is due. And I have posted the notes for 5, 6, and 7 today. And what I plan on doing is to cover that, plus if we have time, I want to go back and do a little bit more in the matrix algebra. So that's the plan today. There's only actually one section left in the book, and that's on logistic regression. And that's what I'll plan on doing here, along with maybe finishing up the matrix algebra. I'm going to perhaps add another example to that, which is why I didn't post it. I'm probably also going to post an example of Poisson regression to give you an idea of the other types of models. There are several things that have not been covered. They've been covered, but several things that I have wanted to add to the course. And so we'll primarily finish, and then next Monday may spend a little time finishing up odds and ends, and then we'll talk about the exam and review the materials. Are there any questions? As best I can tell, the exam is on the 12th of December at 11 a.m. to 1 p.m. Okay. So that is the schedule. So what I want to do now is to go into the notes. So I'll go ahead and leave that there, and I'll bring up our studio. Now, just for a quick reference of what we did. We basically did we covered the basic ideas of multiple regression. But we didn't do what I would call model fitting, which is what we'll do today, along with some other topics. But we went through and we fit models. We looked at the ANOVA table. We also looked at the summary table. And we made inferences about the overall regression model. We have K regressors or K predictors. Then we could test the full model using the error mean square. And that's what I'm showing here. But a lot of times the interest focuses on individual predictors. In other words, in this case, where we're looking at blood pressure, systolic blood pressure, and we wanted to see if that was related to age and weight. If you look at this, you can see the individual coefficients, and you can see the estimates. In that column, that particular column where it says estimates gives the model, the formative model. And then the standard errors for each of the corresponding terms, and the t-test, and then the p-values. You can see that weight is not significant. It has a p-value of over 0.7, whereas age is fairly highly significant. And so you might not know what the residual standard error is. Well, basically, that's the variability about, in this case, it's the regression plane. It's the variability about the regression plane, although it's the square root of that. I give that? Not sure that I have that computed. I computed someplace. Maybe back here. This is where I define it. And this is where I compute the variance estimate, which is the sum of squares of the y's from the y hats divided by the degrees of freedom. And you're fitting k plus 1 dimensions, k predictors plus the intercept, and then degrees of freedom associated with the error is n minus k minus 1. And so that actually turns out to be 74.77 when I compute this. And that corresponds down here in the analysis variance table, which is given here, to this, except that's the square root of it. That's like a standard deviation. So if I square that, I get what I call s squared sub y dot x. And that's the variability of y fitting the x's. And so that 8.65, what they call the residual standard error, is the variation about the, in this case it's a plane and I have points below and above it. And if I take the vertical distance and square them and add them up and divide by n minus k minus 1, that gives me the sum of squares of those adjusted for the degrees of freedom, and then if I take the square root, I get the 8.65. We don't have many degrees of freedom for error here because this is a very small data set. And you can see the multiple R squared is 0.92, 0.918. And then you can see the adjusted R squared, which adjusts for how many terms you fit, is not as large. It's 0.876, but it's still quite high. So we have a fairly good fit. And here I talk about type 1 and type 2 sums of squares using the ANOVA. And the standardized regression coefficients, those are standardized so that they're unitless. So if you look at B sub I, it has units of y over the units of y over the units of x sub I. So S sub I has units of x sub I squared. If I take square root of it, it has units of x. And S sub yy has units of y squared. So if I take square root, it has units of y. So I'm canceling out the units. I'm taking the units of y over x and multiplying by something that has units of x over y. So units cancel out. These are called the standardized partial regression coefficients. And then I show you how to get confidence interval and predictions interval on predicted values. A lot of times it's a good idea. This is y. So this is y on age. And you can see why the linear relationship is much stronger with age than it is weight. And in fact, we only need that in the model. And then if you plot the y versus y hats, you can see that this residual variation, again, if I take these vertical distance and square them and add them up, divide by n minus k minus 1, that gives me the s squared sub y dot x, which is the standard error, residual standard error squared. And this is a residual, so things look pretty good overall. But here's how we compute the adjusted R squared, which adjusts for how many terms you fit. If you have a big n and you only fit a few terms, then the adjusted R squared is going to be about the same as the R squared. But if n is not very big and the number of terms you fit starts approaching n, then the adjusted R squared can be quite a bit smaller. So we want to take into account how many terms we fit. As we fit more terms, in essence, there's a penalty. So that's what we did last time. So what I'd like to do today is primarily cover sections 5, 6, and 7. And it's in the notes under chapter 14, C14S5, but it's actually 5, 6, and 7. So let me bring this up. And I'll set the working directory to be this. Okay. I'm going to go ahead and run this. Now, as I mentioned to you, or maybe I didn't, but R squared, you think of that as a measure of fit. But what happens is that as k gets large relative to n, R squared will go to 1. In other words, as k plus 1, 1 is for the intercept, as k plus 1 approaches n, then R squared approaches 1. So you may think you have a good fit. If you've got a small n problem, if you've got a number of predictors, you may think you have a good fit. But in fact, that may not be the case at all. It may just be the fact that you overfit. So this is what happens to R squared as k plus 1 approaches n. And the adjusted R squared is one way to fix it, which we had. That was the last slide on the preceding .omd file. So that will go up more slowly, and in fact, there's no guarantee that it's monotonically increasing. This is always monotonically increasing, but there's no guarantee that the adjusted R squared. So for example, as a corresponding thing, besides looking at the R squared and adjusted R squared, we want a small mean square error, right? We want it to be small. And if you look at the sum of squares for error, there are various ways you can compute it. But one way is the sum of the beta sub I times the S sub I y. S sub yi is the cross product of the xi with the y. And the sum of squares will always increase as k increases, so it will always get bigger. So this is sum of squares for regression. The sum of squares for regression will always increase as you add more predictors. But on the other hand, I could look at the mean square error, which simply, if I want the sum of squares due to error, I take S sub yy, which is the sum of squares, the total sum of squares adjusted for the mean. And if I subtract from that the sum of squares due to regression and divide by the corresponding degrees of freedom, which is n minus k minus 1, then that is the mean square for error. So you might ask, I would like to have a small mean square of error. But here's the problem. What typically happens as you increase k, the mean square for it decreases to a certain point, and then it starts to increase again. And the reason is you have a diminishing returns. If you put in an x that doesn't explain much variation, then SS sub r doesn't increase much. But you still decrease, in other words, the numerator, S sub r, may barely increase, but yet the denominator, the k, increases by 1 unit. So at some point, the denominator may be getting smaller more quickly than the numerator, in which case you could start increasing again. So ideally what you'd like to do, well, I don't want to say ideally because this is one way you could do it, is pick k that minimizes the error mean square. Now this is kind of simplistic because we often use more sophisticated techniques like cross-validation, which we probably won't have time to cover in this course. So somehow, if you could somehow combine, what's happening at the error mean squared with what's happening in the adjusted R squared, that would be good. And there is a measure similar to that called the Malus CP. And the Malus CP is defined as the reduced model sum of squares. Let me blow this up a little bit so you can see it. It's the reduced model sum of squares due to error, and that's the sum of squares, divided by the full model mean square due to error, which is what we computed above, minus n plus 2p. You can view the 2p as a penalty term. In other words, CP will get bigger. CP will get bigger as p gets bigger. But on the other hand, the reduced model sum of squares will get smaller. But if it only gets a little bit smaller, in other words, if I add another term, and the reduced model sum of square, in other words, if I add a new x, and that new x explains almost no variability, then you won't reduce the sum of squares due to error very much. So the numerator will barely reduce. On the other hand, the 2p will increase. And so again, you can view the 2p as a penalty term. And so what we'd like to do is, you might say, well, I'd like to minimize c sub p, which I think is basically what the book says. That's not quite correct. First of all, you can show that Cp equals p for the full model. So if you're fitting three terms, if p equals 3 is the full model, p equals 3 is the full model, which is the case in the example we were looking at, because you had age, weight, and the intercept, and that p counts the intercept. Then p equals 3 in that case, and for that, and when you do that, then c sub 3 is 3 in that case. So you would like c sub p to be less than p, but almost equal to p. In other words, you'd like to pick a p. You're trying to get simplicity, so you want a small p. You want c sub p to be less than p, but you want it to be relatively close to p. So that's sort of the idea. So there are various ways. I'm going to show you another way you can compute it, but there's a package called LEAPS. So there's a library LEAPS, L-E-A-P-S. That stands for leaps and bounds. You could argue that you might want to fit all possible regressions. Suppose you have 3 predictors. Then you can fit x1 by itself, x2 by itself, x3 by itself. You could fit x1 and x2, x1 and x3, x2 and x3, and x1, x2, and x3. So you could ask, well, how many models do I have? Well, I have 3, besides the intercept. I have 3 things taken one at a time, which is 3, right? So that's x1, x2, x3 by themselves. Then I have 3 things taken 2 at a time, which is 3. x1 of x2, x1 of x3, and x2 of x3. And then you have x1, x2, x3, which is 3 things taken 3 at a time. You also have 3 things taken 0 at a time, which is 1, which is the intercept model with no predictors. So altogether, how many do I have? I have 8. Okay? So you say, well, that's not so bad, but suppose you had 20 predictors. Then you have 20 things taken 0 at a time, plus 20 things taken 1 at a time, plus 20 things taken 2 at a time, plus 20 things taken 3 at a time. It gets to be quite a few. Leaps and bounds does that in a pretty efficient way. It will compute all possible regressions. Now, if you really wanted all of those to fit, suppose you were trying to find the best model. And that's what we're going to be talking about shortly. How do you find the best model? Well, you've got to define what you mean by best. You have to have some criterion of what's best. And we're going to look at several different criteria. So if you're looking at the best model, or if that's what your goal is, if you have a lot of predictors, you have a lot of choices. And some of them are very close. What you want is what's called a parsimonious model. That is, you want a model with as few terms as possible, but not too few. You want to explain most of the variability. You don't want a lot of variables in there that explain very little variation. So we'd like a fairly parsimonious model. In other words, we want p to be reasonably small, the number of terms in the model. But leaps and bounds, we'll do them every model. Now suppose we computed CP for every model. Well, if you look at the way I fit this, I say leaps. I'm doing C-bind, age, and weight, and so this is the X matrix, and this needs to be a matrix, so I say C-bind, age, and weight. And then that's the Y, and then I just assign names, age, and weight. And that's a good idea because down here, if I look at the component of G called which, then it's 1, 1, and 2. Now what does this mean? The first one means that age is in the model but not weight. True, false. Then I have another fit that has one term in the model. And there's that first time is telling you how many terms are in the model. So the next one says there's one term in the model, false, true. That means weight is in there, not age. And then two terms in the model, the two, true, true, meaning both age and weight. So what are the corresponding CP statistics for this? It's 1.167, 18, and 3. Well, that 3 is P. In other words, C sub 3 is 3. That's the full model. That's always true. C sub P equals P. In other words, if I would have 4 predictors plus the intercept, that would be 5. P would be 5, and C sub 5 would be equal to 5 in that case. If I fit the intercept plus the 4 predictors, I would get exactly 5. Well, it's possible that's the model you're going to fit. But you'd hope to fit one simpler than that. Of course, in this case, there are only 2 predictors, so it's quite possible that both of them would have been significant. Now, we already know that weight's not significant. But notice what happens. When age is in the model but not weight, my CP is small. It's 1.167. Okay? And in that case, P is 2 because I have age in the intercept. So I'm below 2 and small. But if I put weight in but delete age, it's 18.167, which is not good. In other words, if I only had weight in the model but not age, I get a very poor fit. Well, it turns out, it turns out you can plot these values, and in this case, there's actually a function called, in the library fairway, there's actually a function called CP plot. But for some reason, it didn't plot this quite. I didn't play with it anymore. I'm going to look at it. I don't know if it's because the scale. I'm not sure why it didn't fit it. It cut the plot off here, so you just saw the bottom part. You didn't see this. Now, that may have been if I would have changed. There's something called YLIM for a plot. And perhaps there's an option in CP plot that allows you to change the scale on the y-axis. But at any rate, for some reason it chopped off that point up there, which is rather important. So these are the single-term models here and here. In other words, P is equal to 2, and that's because I have a single term plus the intercept. When P equals 3, you can see it's 3. Well, I only have 3 values of C sub P here, but in a more complex model, you would have quite a few more. So this would indicate, just based on the CP criterion, that I would choose the model with age in it. Now we're going to look at this a little more carefully in a number of different ways. We're going to look at some selection methods. We're going to look at selection methods in 2 ways. There's a third way that's often used. But we're going to do, first of all, what's called backwards elimination. What you do is you begin with the full model and then you remove variables. And the other one is stepwise, where you add variables. You start out with none and you add variables. But once you add them, if I just added, that would be called forward selection. In other words, if I take the null model and a null of just the intercept and I start adding terms to the model, that's called forward selection. We're not going to cover that. We're going to cover a variation of that called stepwise regression. And that is, once you add terms later on, you could remove them. And the reason that this may happen is because the x's are correlated. So it may be that your best x, once you enter it, at some point later on, it gets correlated with some other x, and it falls below significance, and you remove it. That's sort of the basic idea. Now we're going to base this on the f-test, although you can see R actually is a little more flexible. What we're going to do, we have some, these are the R squared terms. So this R squared sub f means R squared for the full model, and then R squared sub R with a small r means R squared for the reduced model. So if you have a full model, that would be all the terms in the model. And then typically what happens is I drop one term out at a time. I don't drop two out at a time. I drop one out. Then I say, okay, can I drop any more out? So the case of f is the degrees of freedom for the regression for the full model. It's the number of terms. In case of R is the number of terms for the reduced model. Now usually the reduced model just has one fewer term. So case of f minus case of R is equal to 1, because I just drop out one term. So usually you just have the difference in R squared for the full versus reduced. And the reduced usually just has one less term than the full. And then I keep dropping back. And then that's divided by the 1 minus R squared for the full model, which has n minus the degrees of freedom. That's like the error, sort of. That's n minus case of f for the full minus 1. So that's the f-test we're going to use. Now R has a procedure for doing this, and I'll show you how R does it. So what I'm going to first of all do is I'm going to fit the full model. Systolic blood pressure tilde age plus weight. I'll call that model M2. And then I'm going to get a summary for M2, and I call that M2.S for the summary. And I can extract the mean square error, which is sigma squared. In other words, if I take M2.S $ sigma squared, this gives me the mean square error for the full model. Now what can happen is, what happens is that drop 1 says, okay, take the full model, and I'm going to look at all possible choices of dropping 1, and this will give you several different criteria. It will give you the residual sums of squares, it will give you the CP for each of those models, and it will give you the f-test. So, let's take a look at this. So this is my model. I'm doing drop 1. I'm taking M1, the full model, as my starting point, and I'm going to drop each term in succession. Now what it does is it gives you, this says none are dropped. So that's actually the full model. And when I drop none, my residual degrees of freedom is 299, and the CP is 3. You understand why it's 3? Because I have 3 terms. I have the full model. CP equals P for the full model. So that's my base point. Now suppose I drop out age. What happens? Well, this first term is that 1284 is the sum of squares due to regression. Okay. And when I drop that out, that sum of squares due to regression actually goes into the error term. And now what that means is if I take this number to 299 and add to 1284, I get this number. In other words, the residual sums of squares gets much bigger if I drop out age. That means only weights in the model. And notice the CP jumps up. That's that same CP I had above, that 18.18. Do you remember? Look at these CP statistics and then look up here. Here. Rounding slightly differently, but those are the same numbers, actually. So I have an F value, and that p-value of 0.014 was the same F-test that I had above. In other words, I don't want to drop out age. It skyrockets the CP, and if I look at it, if I look at that test for age after weight, it's highly significant. So I don't want to drop it out. But what about weight? Do I want to drop it out? Well, if I look at weight, it only reduces, it only accounts for the sum of squares due to regression for age is only 12. Very small. And so the residual just barely goes up to 312. There's rounding going on here. And notice what happens to the CP. It's 1.17. That's good. So if I drop out age is only accounting for a very small regression sum of squares. The CP is nice. But notice the test for weight is the F value is 0.17 with a p-value of 0.704. Now those p-values are the same. These two p-values right here are the same. I don't know. It may be, it's back on that preceding groups of slides. I don't have it here. Oh, yeah, I do right here. Oh no, we had those same p-values when we computed it back in the preceding groups, the preceding.rmd file. Okay? So this says that we can remove weight from the model without losing much information. So now let's take M2, the model M2, and update it. And notice I say I want to update M2 by adding weight, by subtracting weight from the model. So this is strange notation. I have dot tilde dot. That refers to, the dot tilde dot refers to, the dot on the left means the y variable from M2. Tilde, the dot means the x variables from M2. And so I'm going to take the y variable tilde, the x variables from M2, and I'm going to subtract from it weight. In other words, I'm going to remove weight from the model. So M3 will only have age and intercept. It will not have weight. So that update is a nice little function. That lets you update a model by adding or subtracting terms. And then I'm going to take M3 and see if I can drop anything else. Well, anything else is only age. And so I have a model that says systolic blood pressure tilde age. And notice that the residual sums for not dropping anything, it's 312. Well, where did that come from? It comes from here. Because that was dropping weight. So that's where I start from. The CP is 1.17. Then this says, what happens if I try to drop out age? If I drop out age, I have nothing in the model but the intercept. But I don't want to do that, do I? Because the residual sum of squares now for age is 3316. And it would increase the residual sums of squares up to 3628. So again, this plus this will give you that. So that residual sum of squares with only the intercept is huge. The CP skyrockets. That's not good. But see the F value, and this is the F value of fitting age with nothing else in the model except the intercept, is highly significant with a p-value of 0.00076. So this is a rather trivial example because we only had two predictors. And one's significant, one's not. So that's backwards. That's backwards elimination. But we started out with a pretty small model, so I did one more thing. I did ANOVA M3 and M2, which simply compares model 2 to model 3. So what they call M2 is really systolic. Model 2 is actually the one that has both terms in it. And then model 3 only has age in it. So model 3, what I called M3 is really model 1 in that notation. In other words, this is M3 right here, what's called model 1. This is M2. And then I'm getting the difference in the residual sums of squares, and we can see again that I don't need, model 1 is quite sufficient. I didn't need to do this. I just threw it in to show you another way that you can compare model 2 and model 3, M2 and M3. We've done this before. So that's called backwards elimination. Now, stepwise regression, we do this in terms of what are called the correlations or the partial correlations, which are really the standardized regression coefficients. So what we do is we start with a null model, in this case, and you add x variables that are most strongly related to y. So initially, we look at the correlation between x1 and y, x2 and y, up through xk and y, and we say, okay, which one is the largest correlation? It's not enough to be the largest, it also has to be significant. And so let's suppose that x1 is the model. Then we would say, okay, it has to have a p-value which is small enough. Now, a lot of times with these multiple comparisons procedures, you might think, well, I'm going to look at the p-values and compare them to 0.05. A lot of times we actually are a little bit more liberal because of the multiple testing problem. So we actually often allow variables to enter, and then we may further screen them later. But we may pick a p-value of 0.1. That's not uncommon to use 0.1 instead of 0.05 in these selection procedures. Now, once you have put like x1 in the model, then you might want to ask, what is the partial correlation of y with x2, removing the effect of x1? That's called the partial correlation between y and x2, removing the effect of x1. And you can actually compute this from the simple correlations, and I'm not going to spend a lot of time on this. But the point is, we can compute the partial correlations. Now, R doesn't actually quite do it this way. It's equivalent to this, however. And then we can do t-tests to determine, which variables we should enter, or once we've entered, should we take any out. I think the best way to understand this is look at how R does it, and we're going to look at a slightly bigger example. There's a data set called larvae.txt. What you have is you have grab samples from 30 random sediment locations. And so you grab out a certain amount of sediment in a lake, and you're looking at you measure the depth for that sediment draw. You also measure the brackishness, which is the conductivity of the water, and the dissolved oxygen. And these are, what you're trying to do is to predict the midge count. So the response variable is actually a count, the number of midges. Now, there's always an issue when you have a count to say, well, is this count really normally distributed? And if not, maybe we should transform things. Well, we could check those assumptions to see whether we could fit the model, and then we could look at the residuals and see if they're normally distributed. But if you have a count, then another way you may fit this model is with a Poisson regression. Poisson is a distribution we use for count data. You get 0, 1, 2. So any given sample technically could have 0 midges, 1 midge, 2 midges, and so forth. And so we might want to try this same example using a Poisson regression. But we're going to assume normality. Now, if the counts are large enough, that may not be a bad assumption. But if the counts are near 0, a lot of times you have a positively skewed distribution that looks sort of like a Poisson distribution. So we have midges. The first column, midges, is y, and then I have 3 x's, depth, brackishness, and oxygen. That's actually dissolved oxygen. So LM0, what I'm going to do is to, first of all, fit the model that has all terms in it. And then I'm going to get the mean square error for the full model. So I'm going to get the sigma squared. But a lot of times it's a good idea to plot the data before you do anything else. And this is a Scatterplot Matrix. And you can see, look at the first row. This is y, and then these are the plots for each of the x's. So this is depth, this is midge versus depth, midge versus brackiness, and midge versus oxygen. So what can you see immediately? It looks like there's a positive relationship with depth. The deeper it is, the more midges you find, right? And on the other hand, with dissolved oxygen, the more dissolved oxygens you have, the fewer midges you have. And then it seems like there's not much relationship with brackishness. So we sort of see that maybe there's a positive relationship with depth, a negative relationship with oxygen. Now you might also ask, if I look at the predictors, I might ask, are they correlated? Well, depth and brackishness doesn't seem to be correlated, nor does depth and oxygen. It seems like there's a bit of a negative correlation, though, between depth and oxygen. In other words, as the dissolved oxygen goes up, the depth is going down. So there's a bit of a negative, there's a bit of a correlation, but it's a fairly weak correlation, which is good. Because if the x's are highly correlated, that is what we say they're collinear. And if the x's are collinear, then we have a problem. So we can kind of tell from this graph what might happen. So we're going to fit this full model. And we're first of all going to do backwards elimination. So we fit the full model, and here's the summary of that LM0. Notice that the p-values, that depth and oxygen are highly significant, and that brackishness is not. So if I say drop 1 for this full model, you can see that when I dropped brackishness, notice that the CP is 2.18. Now for the full model, the CP is 4. Why? Because for the full model, I fit 3 x's plus the intercept, that's 4. So for the full model, the CP is 4. It's always, for the full model, the CP is always equal to k plus 1, or the number of predictors plus the intercept. If I drop out depth, that's not good. The CP goes up a lot. If I drop out oxygen, then it goes up a whole lot. But by dropping out brackishness, now notice brackishness only has an F value of 0.18 and therefore a p-value of 0.68. Now that p-value, those p-values here are the same as the ones above. So we can see that what I'm going to do now is take the model, I'm going to take the model LM0, and I'm going to take that same model and subtract out brackishness. And I'm going to call that model larvae.lm1. And then I'm going to try to see if I can drop any more. And so notice the CP, when I have none, is 2.18. And if I try to drop either of these out, it skyrockets. So, and basically, we're finished. So we have a reduced model. I'll do a summary of the OM1. Here's our model. That would be our final model. With both depth and oxygen. But notice that oxygen of the two is more important. They both have very small p-values, but the p-value for oxygen is very, very low. So if I look back here at the graph, that may give us some insight. That's a bit tighter than this one. This has a bit more variability. But together the R squared is about 0.87. And notice the adjusted R squared here is almost, it's not adjusted very much in this case. That's because we had 30 observations. So we have 27 degrees of freedom for the error term for this model. So we have a reasonable number of degrees of freedom, and so we get a very good fit. The R squared is quite high. Here I just did an ANOVA to compare the two models, and this just confirms what we've always done, that the effect due to midge is not significant. Okay. Any questions on that? So that was backwards elimination with a slightly bigger problem. We went from 2 predictors to 3, but at any rate, the same idea holds. Now, what about stepwise? Here we start with the null model. So I'm going to call larva.step0 is just midges tilde 1. That 1 means I'm only going to fit the intercept. And then I'm going to say add 1. I'm going to start with the null model, this model, and I'm going to look at adding from these possibilities. And so when I do add 1, now this is an add 1, not a drop 1. So it's starting with the null model. And then it says, well, what happens if you add depth? What happens if you add depth? Well, it's highly significant. By the way, if I now take the sum of squares due to depth and add it to its residual, I get the residual sum of squares for none. And then for brackishness, it only accounts for 4 sum of squares. And again, the 4 plus the 2920 add together gives you the 2924. And oxygen, it has the smallest residual sum of squares by adding oxygen. Notice the CP still is pretty large, but it's smallest for oxygen. So I'm going to add oxygen first. It's not a small CP, and the reason it's not small is because depth is also important. So I'm going to add oxygen. It has the smallest residual sum of squares. It has the smallest CP, and the biggest F value, and the smallest P value. So I'm going to add oxygen. So what I'm going to do next is I'm going to update the step 0 model to step 1 by adding oxygen to it. So I have tilde dot tilde. That means tilde dot tilde is really the model that only fits the intercept. And I'm going to add oxygen to it. And I'm going to call that the step 1 model. And then I'm going to do an add 1 to see what else I might be able to add. And so here's my model. And I could add depth or brackishness. Well, depth has a pretty large sum of squares. It reduces the residual sum of squares to 369. The CP, as we know from before, is 2.18 now. And then brackishness, it only accounts for 1 sum of squares. The residual sum of squares is barely reduced. The F value is very small, and the P value is 0.85. So clearly, I want to add depth. So what I'm now going to do is call larva.step2. I'm going to update step 1 with depth. And then I'm going to see, I'm now going to do a drop. In other words, I've added 2 terms to the model. It's possible that once I added depth to the model, it's possible that oxygen is no longer significant. But that's actually not true. So I try to now drop 1 from the model, and this is the model, and you can see that both of them are highly significant. I shouldn't add anything. Now if I take step 2 and I say, okay, I want to see if I can add anything else. Step 2 has depth and oxygen. I'm doing a final test to see if I should add brackishness. And the answer is no. You can see here that I should not add brackishness. So this is, again, my final model. Are there any questions? Now, just remember what I did is I added a term. At that point, there's no point. When I add a term, there's no point in doing a drop, because I wouldn't have, if I add it, you're not going to add it and just take it out again. So I waited until I added another term, and then I said, okay, I added a second term. Is it possible the first term I added should now drop out? And the answer is no. So I didn't drop it out. And then I finally did a check to see if I should add the third term to the model. And the answer was no. So I just have the two-variable model. Now, there are a lot of criterion-based models. And if you get into more advanced regression, you get into what are called regularization models that have constraints. And they go by names like lasso, elastic net, ridge regression. These are topics that are called regularization methods. And what they do is rather than just minimizing the residual sums of squares and finding the best fit, they have a penalty term. And that penalty term, it depends on the betas. So it's something like the sum of the absolute values of the betas. You're putting that as a constraint, or the sum of squares of the absolute value, the sum of squares of the betas, and terms like that with some coefficient that's a penalty term. We're going to look at some very simple penalty terms. They're a little bit older than the regularization methods, like the lasso. And this is called the AIC and the BIC. The Hierarchical information criteria is perhaps the most common. Basically, it takes the log of the sum of squares due to error. It's standardized by n. So n is fixed. So it takes this and penalizes it by plus 2p. So as p gets bigger, if the sum of squares due to residual does not get smaller sufficiently enough, then the 2p will get bigger, and so the AIC will get bigger. You want to minimize the AIC. The BIC is exactly the same, but instead of having a 2, it's log n. Now, R allows you to specify k. K is that penalty, which in the AIC, k equals 2. But k equals log n if you are using the BIC. The BIC is the Bayesian information criterion. Okay? So those look very similar, but the BIC penalizes large models more than the AIC. So if you wanted a more parsimonious model, you might go with the BIC. Now in this course, we don't go into sort of the justification for these, but you sort of see intuitively that the first term, as you fit more things, it gets smaller because the residual sum of squares always gets smaller. But if it only gets a little bit smaller, because the term isn't very important, then on the right-hand side, p will get bigger. And so, you reach a point where you're trying to minimize that. So again, you have a situation that when p is small, typically the left-hand side is outweighing, it's getting smaller at a fast pace, but then the AIC and the BIC can start going up again. So you'd like to find the minimum. So there's a function called step. Larva, I'm going to start with LM0, and I'm going to do k equals 2. And so this is going to look at the full model. Its start value for AIC is 83.09. And this says, what happens if I don't subtract out any, if I subtract out brackishness or depth or oxygen? So this is sort of looking one at a time. And I can see that if I subtract out brackishness, well, my residual sum of squares with the full model is 367. That residual sum of squares by dropping out brackishness only slightly increases. Okay, and that's good. So I can drop out, in other words, the AIC is only slightly larger. If I try to drop out depth, however, or oxygen, in particular oxygen, then the residual sum of squares goes up and the AICs get much larger. Now I want a small AIC. So which one do I want? Well, I want the model that subtracts out brackishness. It has a small AIC. And so for the next model, the AIC is this 81.3. It's actually 81.29. It just, it has now depth plus oxygen. And that's the none. If I try to subtract out either of these, the AIC goes up a lot, and these two are significant. So again, by using the AIC criterion of k equals 2, you can see that I end up with the same model. This may have been obvious in this example, but the point is, if you had a lot more predictors, oh, and notice that I didn't have to do anything. It just sort of, it starts out and just sort of works its way down. So if I use step, I can kind of do it very quickly. Now notice that I get the AIC, but I don't get the CP. In order to get the CP, I need to drop one and add one type. You know, the CPs are with the drop one and add one. So when I just do step, I'm getting the criterion that I select. In this case, it was AIC. Any questions? Well, a lot of times we don't have these nice linear relationships. And so there are several types of functions that are very common. You could have a logarithmic curve, an exponential curve, or a power curve. So we might have a function that looks like this. Y is a plus beta log b times log of x. So it's linear in the log of x, not x. So this is still a linear model, a plus. In other words, if you define x prime to be log of x, then this is a linear model, a plus b times x prime. Now an exponential can have several forms. Y is equal to a e to the bx, or y equals a 10 to the bx, or it could be y is equal to a b to the x. Now in the first case, if I take the log of y, that will linearize it as the log of a plus bx. If you know the logarithmic rules, then if I transform the y, then it linearizes it. In the first case, I had to transform the x, not the y. In this case, I'm transforming y. So if you have a logarithmic function, you can usually correct it by transforming x. Whereas if you have an exponential function, you can usually transform it by transforming the y. So when I take the log of y, if I have y equals a e to the bx, and if I take the natural logarithm, then y prime, where y prime is the log of y, is equal to the log base e of a plus bx. Now what about if I have a 10 to the bx? Again, if I take log base 10, I would have y prime as log base 10. In this case, y prime is log of a plus bx, where the log is again base 10. Now, but log base 10 and log base e are proportional. And then I may have a model that looks like y is equal to a x to the b. In that case, I need to log both x and y. So I take the log of x and the log of. So in other words, the log of y is equal to log of a plus b times the log of x. So I'm transforming both x and y. And so what these exponentials sort of look like this. And it's if b is greater than 0, they're going up. If b is less than 0, it's exponentially decreasing. So we have an exponential increase with b greater than 0 in all cases. The final form is a power function. Suppose I have a model y is equal ax to the b. Now that's different than the one above it, which is a b to the x. So I have y x to the b. So x has a power b. So you might ask, what does this graphically look like? Again, it depends upon b. When b equals 1, it's just linear, right? It's just ax. But when b is greater than 1, it has an exponential. but it's not base E or 10. And if B is between 0 and 1, then it's sort of flattening off. So those are called power curves. And you can often correct those by taking, I'm sorry, I was off on this. That's where you take the log of both of them. I'm sorry. So in this case, you have the log of both. And that is the log of x and y. Here you have a log, but it's the log of b. It's a log of a and log of b when you have ab to the x. You're taking the log of a and log of b. So you're fitting a model that really still only transforms y, not x. But in the power one, you're transforming both x and y. What I'd like to do is to take a look at an example. So suppose that you're modeling the relationship between dose and specific activity dealing with chromosome damage. So the dose is a measure of specific activity, and you want to see how that affects chromosome damage. And so we're going to read in a file called dose.txt, and to print it out, just printing out the first 5 observations, you can see the dose, and here we have the chromosome damage. Now, if you look at it graphically, which I'd always recommend you do, here I'm looking at x, which is a specific activity, versus the chromosome damage. You can see that the chromosome damage is increasing, but notice that it's sort of leveling off. Do you see what I'm saying? It goes up, but it's starting to level off. It's going up at a slower pace. That would indicate what type of transformation? Well, that would be that first one. It's a logarithmic type function, something like that. Not quite that extreme, but it's along those lines, where I transform x by the log. So what we're going to do is I'm going to fit a model, the chromosome, the damage tilde log base 10 of ACT. Now I could have done log base E, but. And so if I get a summary, if I get a fit now, I can see that this is highly significant. Now it's very possible I didn't actually fit the model without transforming, but you're going to get a fairly good, if you fit a straight line through that, it's not going to be terrible. But this might be slightly better. So what I do is I'm fitting the log base 10 of ACT, and I can see that it's highly significant. And if I do an ANOVA on it, I just get the f-test version of that. So I'm going to plot the log base 10 of ACT versus chromosome. Now you notice when I do that it's pretty well straightened out. We don't have that curvature that's leveling off. And then the AB line, dose.lm, that actually fits the fitted line. Dose.lm is a model object, and if I say AB line with dose.lm, it will fit that model object. It will fit the straight line. So you can see that that's a pretty good fit. So it appears that taking the log of x, notice how things are much more evenly spaced here. Look back here. There's a big gap. The gap between x values keeps getting bigger. And by taking the log of it, base 10, it made the gaps about equal. So it shrunk these gaps between each of the x values. You were going from 40 to 80 to 160 to 320. I think you were doubling it each time, you see. You were going from 40 to 80 to 160 to 320, I believe is what it is. So you were doubling the dose each time. So this brings it into the case where they're more equally spaced. So that was a case where we transformed x. Now let's look at a case where we actually transform y. So we're going to be looking at, this time, we're going to be looking at the diameter of fruit x and the residual insecticide it might be something like A10 to the BX. So we're going to be looking at the residual insecticide, which might be something like that. Well, if you look at the data, we have diameter and residual insecticide. So what happens? As the diameter gets bigger, okay, then you have more and more residual insecticide. You can see that this looks somewhat, I mean, this is a little bit off here, but it basically, you see you have an exponential curve going up. Now, I want to mention to you that in all of these cases, you could fit what's called a nonlinear model. Nonlinear model, you don't get these nice normal equations where you have a set of, linear equations in k+1 unknowns or something like that. You don't have that nice system of equations. And when you have nonlinear models, you have to solve it using calculus techniques. And it's an iterative procedure. You can't solve it with simple matrix operations. You have to solve it using numerical techniques to minimize the sum of squares of residual. It's not the simple minimization that you get in this case. It appears, though, that in this case, if we take the log of insecticide, so I'm taking the log of the y, tilde diameter, it appears that, first of all, it's highly significant. Diameter is highly significant. And notice that when we do this, and now what I have done is plotted the diameter, which is x, versus the log base 10 of insecticide. And then I plotted the fitted value, and you notice that that does a pretty good job. We have a fairly good prediction model by this transformation. Are there any questions on this? So this was an example where we transform the y. Now I don't have an example where you transform both x and y, but again, there may be cases that you want to. That was the power transform. There may be cases where you want to do that. Okay, the final topic is polynomial regression. So, suppose you want to know the relationship between fertilizer and insulin yield per acre. So you have different levels of fertilizer, and you'd like to know how that affects the yield. So, so if you sort of naively said, okay, let's fit a linear model, tubas.linear, where I just do yield tilde fertilizer, and then I do an ANOVA, and you can see that fertilizer is not significant. But look at the graph. This is what we fit. We fit a straight line. But you might guess that if you over-fertilize, it can be destructive. In other words, fertilizer can help up to a point, and then it starts to be destructive. You burn the crop, in essence. You have too much fertilizer. So you can see that. You can see that for low fertilizer, the yield is low. It goes up from 0 with no fertilizer. It goes up at 4, and then it stops dropping down at 8 and 12. It stops to drop down. So you have what looks like a quadratic relationship. So if you were a researcher, you might want to run an experiment to say, well, what is the optimal amount of fertilizer that you should have? So first of all, let's look at a model where we have yield tilde fertilizer. Now notice I'm going to say fertilizer. I actually want to just do arithmetic multiplication. I want to square fertilizer, and that I protects you. And if I have an asterisk in the model, R thinks that means, if I have like A, suppose A is a factor and B is a factor, do you know what A asterisk B means? It means A plus B plus A colon B. Well, that's not what I want. I actually want the squared fertilizers values. You have to put that I, which I think means the identity function. You have to put the I to protect it so that it becomes an arithmetic multiplication, not a model, a model symbol asterisk. So the asterisk here will mean arithmetic multiplication. So you have to put that I, and I'm going to fit a quadratic. That's tubus dot quadratic, so it fits the linear and the quadratic term. Now notice what happens. That the quadratic term is significant. The p-value is 0.019, whereas the linear term is not. So if you were thinking in terms of what we just did, you might say, well, should I drop out the linear term? And the answer is no, even though it is not significant. I'm building up hierarchically. And if by dropping out the linear term, then that's going to have an unexpected consequence on the model. This is what we call a hierarchical model. It's sort of like saying that if I have A and B, and they're factors, so I can think of the model A plus B plus A colon B, and if A and A colon B is significant, but the main effects are not, should I drop out A or B? And the answer is no, even if A or B are not significant. It's the same idea here. And so we're going to leave in the linear term. Now, the next question might be, well, is there a cubic term? So I'm going to add a fert times fert times fert, so I'm going to get a cubic term in here. Now notice that the cubic term is not significant. Now it's okay to drop out a higher order term, just not lower order terms. So I am going to drop, I don't need the cubic term, but I do need the quadratic, and because I have the quadratic, I need the linear. So my final model will be the model for the quadratic one here. So I'm going to get a summary of the tubus.quad, and this actually gives me the regression. Right here is the regression equation. Whoops. That's the intercept, that's the linear term, and that's the quadratic coefficient. Okay, so I have like y is equal to a plus bx squared, well, plus cx squared. And so that's my model. Notice in this case, that for my t-values, let's see, why is that significant? Whereas the preceding one wasn't. What was I wrong? Oh, this is a type 1 sum of squares. Fertilizer by itself is not significant. If I add quadratic, yeah. This is something that you have to realize. Remember, R does type 1 sums of squares. So when it's fitting this, it's fitting fertilizer without quadratic. It's not significant. Then it's fitting the quadratic after the linear. It is significant. When I do this is testing fertilizer after the quadratic and the quadratic after the fertilizer, in which case both are significant here. Now, what I'd like to do is here's where I want to get. I only have 4 fitted points here, 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 and here. I only have 4 x values, right? 4 levels of fertilizer. So what I'd like to do is to find the maximum. I'd like to find the maximum. I'd like to find the fertilizer amount that corresponds to the maximum yield. Now, as you can see, that this is really not the maximum, nor is this. The maximum is some value. If the true quadratic model looks like the dashed line, then the maximum is not here or here, but it's someplace here. Now how can you find the maximum? Well, I have a model that looks like this. Y is equal to b naught plus b1x plus b2x squared. So what you do is we take the derivative of that model with respect to x and solve for x. And I think it's minus b over 2, minus b1 over 2b2 or something like that. In other words, that's a simple polynomial, and if you know any calculus, then you could easily take the derivative of that and set it equal to 0 and solve for x. And if you did that, you would find out that x is equal to 6.48. Okay. So we had measured it as 0, 4, 8, and 12, but the maximum is actually about 6.5. Now, here's my model. I take the quad model, $ coefficient 1, that's the intercept, and this is B1 and this is B2. So I'm taking B naught plus B1 times 6.48, that's the value of x, plus B2 times 6.48 squared. And that will give me the y value at the maximum. So by calculus you can find 6.48 as the x value that corresponds to the maximum, and the actual maximum is given to y sub m. And so that's what these vertical lines are. The vertical lines at x, there's a vertical line at xm and a horizontal line at ym. So this line right here, that's the x value corresponding to max, and that's the actual max right here. But I also want to plot the lines, and I do two things. The first one says lines fert tubus dot. This is the fitted line. Well, the fitted line only occurs at 4 places, and so this solid line that's segmented, that's from this first command lines. That actually fits the model at the 4 points. It gets the predicted value, and it does a linear interpolation between the points by default. But I don't really want a linear interpolation, do I? I have a quadratic model. And so I define an x. I said x, I want a sequence from 0 to 12 by 0.1. So this is a sequence from 0 to 12 by 0.1s. So what I'm going to do is I'm going to fit another one, lines of x, which goes 0, 0.1, 0.2, and so forth up to 12. And then I'm going to take this model, coefficient 1 plus b naught plus b1 times x, and x is a vector now, going from 0 to 12 by 0.1s. And then this is x squared. And I'm going to, line type 2 means dashed. And so that's actually what fits this nice smooth curve. So that's how we do it. If the quadratic is reasonably correct, then we achieve a maximum of about 6.5, which was not one of the ones that we actually measured. We measured 4 and 8. But we don't want to just do linear interpretation. If we would have done linear interpretation, we would have been right here, which is below what maybe the actual yield would be at the maximum. So that's kind of an interesting thing. Now, if you went kind of one step beyond this type of model, a polynomial model is still linear in the parameters. So when we say linear, we mean linear in the parameters. So it's linear in beta naught, beta 1, beta 2. But suppose it's nonlinear in the parameters. So there was something a little bit hidden here. When I go back up here, you may say, let's take this exponential right here. What happens when I take the log of a product? The log of A times B. What is it? It's the log of A plus the log of B, right? Now, what's missing from this model, y equals a e to the bx? What is missing? The error term, the epsilon. Suppose the epsilon is additive. Can I do that transformation? This transformation depends on the fact that the epsilon is multiplicative. The real model is this. Y is equal to a e to the bx times epsilon. And therefore, when I take the log of it, what does it become? It becomes y prime, or the log of y equals the log of a plus bx plus the log of epsilon, if it's multiplicative. But if that epsilon is additive, it won't work. If that the only thing I have to do is say the error term is additive. I can't take the log. And that is a nonlinear model. So if my model is y is equal to a plus e bx plus epsilon, I have to solve it as a nonlinear model. So we're assuming by taking the log that there's a multiplicative error term. That's a key point. So if it's nonlinear, then you say, well, how do I solve it? Well, it's quite a bit harder. In fact, you can't solve it in closed form. You have to iterate the solution. You have to do a numerical solution. You can't solve it. You don't have a nice system of linear equations, of k plus 1 linear equations and k plus 1 unknowns that you can easily solve using linear algebra techniques or matrix algebra techniques. You can't do that. You can approximate it. If you take a curve and you can approximate the solution by linear tangents to that curve, but you have to iterate till you find the actual solution where there's a minimum. So for example, when I had this curve up here, this is just to illustrate the point. If I were trying to find a minimum here, and if I knew the function, then there are numerical techniques of finding it. And that's what you have to, this is mean square error, so this is not, this is not a database problem. Well, it's database, but it's a mean square error. But what I'm really talking about is the functional form of the model. That you would have to find the solution. Yeah.
Oh, it's 1.
Oh, okay. Oh, I'm sorry. Okay, well, this finishes it off. We didn't get to matrix algebra, so what I'm going to do is cover logistic regression next time together with, sorry for keeping you late, which I do too many times. But at any rate, that's it. So we don't have much more to cover in the book.